In this video, we're going to discuss an algebraic technique called partial fraction decomposition. So to give you a sense of how this technique might be used, let's do a type of problem that you're probably familiar with. So we want to add together these two rational expressions. We want to perform that addition. So in order to combine two rational expressions with addition or subtraction, we know we need to have the same denominator. In this case, we don't. So this problem starts by finding a least common denominator. So these two denominators don't have any factors in common, which tells us that our least common denominator is going to have to contain both factors. So our least common denominator will be x plus 2 times x minus 5. And in order to convert each of these rational expressions to a form containing that denominator, we'll have to multiply on top and bottom by whichever factor we happen to be missing. So in the case of the first rational expression, we have the factor x plus 2, we need the factor x minus 5, so we'll multiply the numerator and denominator by that factor. And then for the other rational expression, we need the x plus 2, so again we'll multiply top and bottom by the x plus 2. So that's going to give us 5 times x minus 5, and if we go ahead and combine, we're combining the two numerators with addition, so plus 3 times x plus 2, and then all of that is now divided by our common denominator of x plus 2 times x minus 5. Okay, and then the goal at that point is then to simplify our numerator, so we need to distribute the 5, distribute the 3, and then we can combine our like terms. So that's going to be 5x minus 25 plus 3x plus 6, and then we have the option of either leaving the denominator factored or we can distribute if we want. For the time being, let's just leave it factored. So x plus 2 times x minus 5, and then assuming we want to leave that denominator fully factored, all we now have to do is combine our like terms in the numerator. So 5x plus 3x is going to be 8x, and then negative 25 plus 6 is going to be negative 19. And then we have that denominator of x plus 2 and then x minus 5. And again, we could either distribute in the denominator or we could leave that as is, in which case we're finished. Notice that our numerator, these two terms don't have any common factors. We can't factor, which means there's nothing we can reduce with the denominator, so we would be finished. This would be the rational expression that results from the addition of these two original ones. So just as the distribution of two or more polynomials, just as distribution results in a more complex polynomial, we could say that the addition or the subtraction, depending on the situation we're in, the addition or the subtraction of two or more rational expressions typically results in a more complex rational expression. So we took two relatively simple rational expressions, and by adding them together and thereby going through the least common denominator procedure, we ended up with a rational expression that's arguably more complex than the original two. Now, just as the process of distribution can be reversed, so can the process of rational addition, rational subtraction. We have a specific name for the procedure if we perform it on a polynomial. So if we want to reverse a distribution, take a more complicated polynomial and then break it down into simpler polynomials, then we would attempt to factor it. We call that factorization. We would attempt to factor it. Now, if we wanted to essentially do the same thing for a rational expression, the idea is that we want to work backwards and go from our more complicated expression to the two original expressions that we added together to get this more complicated expression. That is the procedure we call partial fraction decomposition. So we're decomposing this more complicated rational expression into these original fractional terms that could then be combined to give us this more complicated one. And this is going to be a skill you use in integral calculus, taking a more complicated rational expression, breaking it down into simpler ones, specifically ones where our denominators are fully factored. They can't be factored anymore. So finding this partial fraction decomposition is actually a fairly complex procedure. One thing that's important to notice is, okay, if our denominator is factored, then maybe we could determine that our two original denominators have those two factors. If this denominator weren't factored, of course, we would need to factor it in order to find those two original denominators. But here's another thing to notice. Notice that the numerators we started with were both constant numerators. And yet, when we combined everything together, the numerator we ended up with was actually linear. It wasn't constant. So then the question becomes, if you started with this linear numerator, how would you determine that you get back to constant numerators if you wanted to decompose this rational expression into two simpler rational expressions? How would you determine that these two numerators would be the ones you would need? Because otherwise, 5 and 3 don't seem to be very clearly related to 8x minus 19. So even though the denominators might be fairly straightforward to predict, how would you determine what the numerators would have to be in order to decompose your rational expression? Well, that's going to be part of what we do when we find the partial fraction decomposition. So there's going to be two major steps anytime we want to decompose. So first thing we're going to do is we're going to set up the structure of our partial fraction decomposition, which I'm going to just refer to as PFD for simplicity. And we're going to set up that structure using the denominator's factors. So if we're starting with our more complicated rational expression, the first thing we're going to want to do, if it hasn't already been done for us, is we're going to want to take that denominator and we're going to want to factor it. Depending on what the factors look like at that point, that will lead us to a specific structure for how our partial fraction decomposition would look. So that's going to be the first step anytime we want to decompose a rational expression. Then we have to solve for the matching numerators that make our expressions equal. In other words, if we have this rational expression and we know that structurally speaking we should have two smaller rational expressions that contain each of these factors, we then have to answer the question, well, what do the numerators have to be over these two denominators in order to make both of these expressions equivalent? That's going to be the second step in finding our partial fraction decomposition. And this is typically going to require a system of linear equations. So we'll use what we know about systems of equations. The good news is typically if we have to solve a system, it's usually a very simple system to solve. It's usually very straightforward. It's not going to require any particularly advanced techniques. You probably won't need a matrix. More than likely you can just do it using basic substitution. So first let's talk about setting up the structure for our partial fraction decomposition. So if this hasn't already been done, already we need to start by factoring the denominator completely into linear factors and otherwise into irreducible quadratic factors. Now, what do I mean by irreducible? Irreducible, typically if we see something quadratic, we can attempt to factor it further. An irreducible quadratic is one that can't be factored further over the integers. In other words, you would need the quadratic formula to do anything further with it. So if it's the kind of quadratic that you would need the quadratic formula to find its roots for, then you know you're done and you can just leave it alone. So something like x squared plus 1 that doesn't factor any further, that would be considered an irreducible quadratic. If you factored your denominator and you ended up with something like x squared plus 1, you could just leave it alone and you know that's fully factored. Now for each of these factors, we're going to set up a fraction representing a portion of our partial fraction decomposition. So the type of fraction we're going to have to set up is going to depend on the type of factor we're looking at. So if we have linear factors, so this is going to be a general linear factor, ax plus b, so notice it's basically in slope-intercept form, potentially a repeated factor, so we may have that particular factor repeated a certain number of times indicated by our exponent. That portion of our partial fraction decomposition associated with that individual factor is going to look like the following. So we'll start with a denominator of just this factor, and then our numerator will be a constant. We'll call this capital A sub 1. Now we also have to have a fraction that has a denominator of that linear factor, but rather than being linear factor just by itself, it's going to be the linear factor squared. Now that's also going to have a numerator that will be constant. And then we'll repeat this structure, so on and so forth, until we have enough fractions to cover this exponent. So if m is our exponent, that means we're going to have m fractions associated with this particular factor that happens to be repeated m times. So the final fraction we'll need for this particular factor, however many times it's repeated, is going to be m fractions. And notice again, each of our numerators is going to be a constant. So each of these values represents a constant. Now suppose we only have this factor one time. That means that m is an understood 1. That means we'd only need one fraction to go with it. If we have this factor, and for instance it's squared, we see it repeated once, that means we would have 2 fractions associated with it. If it were cubed, we would have 3 fractions, and then so on and so forth. Now we see a similar pattern if we have quadratics. So we're assuming this is an irreducible quadratic factor. In other words, it's something that we can't factor any further without using the quadratic formula. And again, it may be repeated a couple times. So say we have x squared plus 1, but we see that factor maybe 2 or 3 times when we factor our original denominator. Same idea. We're going to have a fraction representing each power of this particular factor. So our first denominator will just contain the factor, just the one time. And then because our denominator is now quadratic, the numerator we're going to look for is actually going to be linear. So it's going to be something of this form. So quadratic denominator, linear numerator. Now we also need to, again, repeat this factor however many times we see it. So if we see 1, we need to have something squared, something cubed, so on and so forth, up until we have enough factors, or excuse me, fractions, to represent how many times this factor is repeated. So for the next fraction, we're going to have a denominator of this irreducible quadratic factor, but it's going to be squared. And then again, we'll have a linear numerator. So that will be something of this form. Again, linear, but now potentially we have different constants. And then so on and so forth, indefinitely, until we've covered all the fractions we need reaching this particular exponent. So our final denominator will be ax squared plus bx plus c to the n power. And again, we have a linear numerator. Now there's a lot of variables here and very few actual constants. This subscript notation, notice the subscript we use corresponds to whatever exponent we have on our particular denominator. So in this case, this would be the factor raised to the first power, so we have a sub 1. This is the factor squared, a sub 2, and then so on and so forth. The reason we use this subscript notation rather than just calling this a, b, c, d, so on and so forth is this general form allows us to accommodate any situation regardless of how high the exponent goes. This particular structuring of our general form allows us to go on indefinitely to however large our exponent ends up being. Same thing down here. We can repeat up to n times, and so notice our subscripts again are corresponding to whatever the exponent happens to be for that particular denominator. So if we're looking at this denominator's factor just one time, we have b sub 1 and c sub 1. If it's twice, b sub 2, c sub 2, and then so on and so forth. Now when we actually look at a problem with some actual concrete numbers, we're not going to have to use this notation. We'll just use however many variables we need, which typically means we can just use a, b, c, d, e, so on and so forth. Okay, so in general, what are we seeing here in terms of a pattern? Well, first, notice that every numerator is 1 degree less than the associated factor in the denominator. So if the factor we're looking at is linear, in other words, x with a power of 1, then our numerators, the associated numerators, will all be constants. We won't have an x associated with that particular numerator. Now, if the factor we're looking at is quadratic, it has a degree of 2, that means our numerator is going to be linear. It will have a degree of 1. If for some reason we had something cubic, which of course is possible, then that means our numerator would have to be quadratic. Now we're going to restrict ourselves to quadratic denominators as our most advanced case, but generally the idea would keep going. If we had quadratic denominators, then we'd have to have, quadratic denominators would be linear numerators, cubic denominators would be quadratic numerators, and then so on and so forth. So that pattern is going to continue regardless of the situation we're in. So every numerator, what we're ultimately having to solve for, is going to be 1 degree less than the degree in the denominator. And then as for repeated factors, if we were to see this linear factor repeated or this quadratic factor repeated, you're going to need a fraction representing each power of that repeated factor up to the highest one that we see in our denominator. So once our denominator is fully factored into these individual factors, we have to repeat this procedure for each of the individual factors. So suppose our denominator has 3 factors. Well, we have to structure the individual fractions in our partial fraction decomposition for every single one of those denominator factors that we see. So if there were 3 of them, we'd have to repeat this procedure 3 times. If it's a linear factor, we'll follow this pattern. If it's a quadratic factor, then we'll follow this pattern. So let's do some practice just setting up the structure, and then we'll take it one step further and we'll actually solve for the matching numerators, and we'll finish our partial fraction decomposition. So let's start with a basic one where everything is already factored. So we have a denominator. This denominator would have been quadratic if it had been distributed out, but it's already been factored for us. So notice each of these individual factors is a linear factor, and we only see each of the factors 1 time. So because they're linear factors, we're going to follow this particular pattern as established. In other words, every numerator is going to be a constant numerator. And then because the factors don't repeat, we only see each factor 1 time, that means we're only going to need 1 fraction to go with each of the individual factors. So for the factor 2x plus 3, which is linear, we only see it 1 time, so we only need the 1 fraction to go with it. So we'll have 1 fraction that has a denominator of 2x plus 3. And then because, again, it is linear, the numerator associated with this denominator is going to have to be a constant. And we'll just call it the constant a. So that's going to be the portion of the partial fraction decomposition corresponding to this factor in our denominator. Now we also need a fraction associated with this second factor, x minus 2. We only see it 1 time, which means we only need 1 fraction to go with it. Again, it is a linear factor, which means the numerator associated with it is going to be a constant numerator, and we can call it b. So this covers both of the factors, the number of times they appear. So this will be the full structure for our partial fraction decomposition. Now the question then becomes, what are a and b so that this relationship is true? And that's what we'll look at next. So we want to practice just a little bit with the structure first, and then we'll talk about how we actually solve for a and b given this particular structure. Okay, let's look at one that's slightly more complicated. So now our denominator is not factored, and it's a cubic denominator. So before we do anything else, we need to factor that denominator. We don't need to do anything with the numerator. So you see that numerator, you see it's quadratic, you may think, hey, I want to factor that. You don't have to worry about factoring that. All we're focused on is what's going on in the denominator. So whenever I need to factor something, a good habit to get into is to always look for a greatest common factor first. That will typically make the factoring problem a little bit easier. So I notice here that each of these terms has an x in common. So I'm going to start by factoring out that x. And that's going to leave me with x squared plus 6x plus 9. Okay, and then I'll just put ... for our numerator. It's the same thing. Again, we haven't done anything with the numerator. Now notice what we're left over with is now quadratic. So it's either a quadratic that we can factor or it's irreducible, which means we'd leave it alone. So we need to determine, can we actually factor this quadratic? So we're looking for numbers that multiply to give positive 9 that would also add to give positive 6. And those two numbers would be positive 3 and then positive 3 again. So what that means, we call this a perfect square trinomial. In other words, it factors into a binomial squared. So the full factorization for our denominator would have a repeated linear factor. Because this particular quadratic factors into a duplicated binomial, we can write it as x plus 3 squared. And this puts us into a slightly different position than we were above. So all of our factors are linear. Don't forget the x. The x is linear. It has an exponent of 1, so it is linear. And then x plus 3 as a factor, as a repeated factor, is a linear factor. But whereas both of the factors were different, they were unique here, x plus 3 is repeated. So we have a repeated factor here. That's going to change the structure for our partial fraction decomposition. So we want to go through all the factors in the denominator. First, the factor x, and then the factor x plus 3, which happens to be repeated. And we want to write the portion of the partial fraction decomposition associated with each of those. So let's start with x. X is a linear factor. We only see it one time, so we only need one fraction to go with it. And because it's a linear factor, the numerator will have to be a constant numerator, so we'll just call it a. Now x plus 3, again repeated 2 times, is also a linear factor, but because we see it 2 times, we're going to have 2 fractions associated with it. So the first fraction, the denominator, will just have an exponent of 1. It'll just be the single factor. Because the denominator is linear, the numerator will be a constant. So we see the x plus 3 the one time, and then we have to have an additional factor, or excuse me, an additional fraction to indicate that this factor is duplicated. So our next fraction is going to have the denominator of x plus 3 squared. But again, the factor itself is linear, so the numerator is going to be a constant. So notice here we end up having 3 fractions, and if we were to write this out, what this really means, x plus 3 squared means the factor x plus 3 is repeated. We have 3 factors, so we have, count them, 1, 2, 3 fractions, and this is going to be our partial fraction decomposition. Okay, let's look at a couple more. Okay. Same kind of thing. We have something cubic in the denominator, and it's not factored, so we want to factor it. Leave the numerator alone. You don't have to do anything with it. So again, look for a greatest common factor first. We have a common factor of x in our denominator, so I'm going to factor that out, and that leaves me with x squared plus 4. Okay, and then again, the the quadratic numerator we just bring over. Okay, so the x, that's linear. Now we're left with something quadratic. Can it be factored? Well, x squared plus 4, a sum of squares cannot be factored. If you tried to solve for x by setting this equal to 0, you're going to run into complex numbers, so this cannot factor. The only way you could factor this perceivably would require the use of complex numbers, and in some ways you would need the quadratic formula in order to handle that. So that means this is an irreducible quadratic. We can't do anything else with that one, so we just leave it alone. So again, this presents a different situation with respect to our partial fraction decomposition. Now we have 2 factors. Each of them only appears one time. So we see the x one time, we see x squared plus 4 one time. which means each factor is only going to need one fraction to go with it. So for our x, it's linear. We only see it the one time. So because it's linear, we have a numerator that is a constant. And then for our x squared plus 4, again, an irreducible quadratic, we can't factor that. It's quadratic, which means the numerator is now 1 degree less than that, which would be a linear numerator. So rather than a constant numerator, it's a linear numerator that we can write in slope-intercept form. So we can write that in the form bx plus c. And again, we only see this factor the one time, so we only need the one fraction to go with it. So this is going to be our partial fraction decompositions form in this case. Okay, let's look at one additional situation. Now, this denominator is factored. We have a quadratic that's repeated. Can we factor this actual quadratic in the denominator? Well, if so, we're looking for numbers that multiply to give positive 5, that also add to give positive 2. Well, the only factors of positive 5 would be positive 1 and positive 5, or negative 1 and negative 5. Neither of those pairs add up to give me a 2, which means that this quadratic is irreducible. We can't factor it anymore. So that means technically this part's done. In terms of factoring, this portion is done and the denominator is fully factored. So now we just need to write the form for our partial fraction decomposition. So we have a quadratic factor and it's repeated 2 times. So because it's repeated, we know we're going to need 2 fractions. And because the factor itself is quadratic, each of the numerators has to be 1 degree less than that. So our first denominator is going to take our factor, and we're only going to have an exponent of 1 on it. We're just going to see it the one time. And again, it's a quadratic denominator, which means the numerator is 1 degree less, which would be a linear numerator, which we can write as ax plus b. Now, because that quadratic factor is repeated, we need an additional fraction that represents this factor, but the factor squared. So x squared plus 2x plus 5 quantity squared. But again, our denominator's factor is quadratic, so the numerator will be a linear numerator. So we can call that cx plus d. And so how many individual constants do we need to solve for in each of these cases now that we have these structures? Well, for our first partial fraction decomposition, we have 2 variables. We need to solve for a and b, so we only have 2 here. For our second one, we have to solve for a, b, and c, so 3 unknowns. For our third, we also have to solve for a, b, and c, but in a different form. Before it was 3 constant numerators, now it's 1 constant numerator, 1 linear numerator. And then for this very last one, 2 linear numerators, which means 1, 2, 3, 4 potential constants that we have to solve for. So at that point, what we need to do is we have to actually solve for those. We have to determine what would the values be for each of these unknown constants to make this relationship true. So that if you were to think of taking these 2 rational expressions and then combining them together, that would result in this original, more complicated rational expression. So essentially, it's a factoring kind of thing. If distribution is reversed by factoring, then partial fraction decomposition reverses taking 2 rational expressions and adding them or subtracting them. So now let's talk about how you would actually do the decomposition. Once you've structured it, how do you determine what those constant values are going to have to be? So we're going to assume that you've already set up that structure, you know what the form is going to be, you know how many variables you're going to have to solve for, and then so on and so forth. The first thing you're going to do after that is you're going to multiply both sides of the equation by the least common denominator across the whole problem, which will result in clearing all fractions. In other words, all the denominators will be eliminated. Now, once that happens, what you're going to have are a bunch of matching like terms on either side of your equation. Everything on the left-hand side will represent the original numerator for your original rational expression, and then everything on the right-hand side will represent what you got from your partial fraction decomposition from its form. So you're going to set up a system of equations by matching all of those like terms on each side of your partial fraction decomposition equation. You're going to write an individual equation for each of the matches. So in other words, if you were to look at the one above, just in general, we have a quadratic term, we have a linear term, and we have a constant term. Any term that's related to a quadratic on this side, you're going to match up with this individual term. Anything related to a linear term on this side, you're going to match up with this term. And anything related to a constant on this side, you're going to match up with the constant term. And that's going to give you a system of equations. Each individual match will result in one equation. And so once you have that system, you're going to solve the system. And again, for one like this, where you have 4 variables, it may originally seem like it will be complex to do so. But in most cases, the original equations you set up as part of that system are going to be very, very basic, very simple, very small. And so solving your system is usually pretty straightforward. So you're going to solve the system, giving you the values of those individual variables, and then you're going to resubstitute those values into the partial fraction decomposition form. In other words, when you know what A, B, C, and D are based on solving your system of equations, plug them back in, and then the resulting expression represents the partial fraction decomposition. It represents the numerators and matching denominators that would split up in such a way to decompose the original rational expression that you started with. Now, the good news with this kind of procedure is just like with factoring, there's always a way to check your work. If you factor and you want to check your work, well, you just redistribute and you make sure you get what you started with. If you get back to what you started with, that means you have a correct factorization. Same kind of thing here. You can always check your work by combining the resulting rational expressions, what you are proposing as your partial fraction decomposition, recombine them using the least common denominator. In other words, do essentially what we did on the first page. Where is it? Can't find it. Oh, there it was. Okay. So essentially, take this is your partial fraction decomposition, and verify that when you recombine, you get the more complicated rational expression you wanted. As long as that's verified through use of our least common denominator, then that's a guarantee that your partial fraction decomposition is correct. And ultimately, that's an optional step, but particularly as you're learning to use this procedure, learning to complete this procedure, it's worth your time to check your work at least maybe once or twice. So let's take those original ones that we set up. We set up 4 different decompositions, each one with a slightly different form. And let's actually complete the decomposition. We want to actually solve for those values. Okay, so to recap what happened with this one. This was our first one that we set up the structure for. We had 2 different factors in the denominator. Each one only appears one time. They're each linear, which means we split it up into 2 fractions. Okay. And each of the numerators was a constant. And if you need to, flip back over and verify that that's correct. Okay, so what I now have is an equation that I want to solve, but normally I want to solve for x, right? I want to solve for x. Well, here that's not the goal. Here the goal is to solve for a and b so that this relationship is true. In other words, if I were to combine these 2 rational expressions together, I want to know what a and b would have to be so that when I combine, I would end up with a numerator of 4x minus 15. So here's what I'm going to do. I'm going to take both sides of this equation and I'm going to multiply by the least common denominator. And what you're going to find when you do that every single time is that your least common denominator is actually the denominator you started with on the left-hand side. It's going to be the original denominator for that original rational expression. So just to save a little space, I'm going to write it like this. I'm going to put brackets around the whole equation, and I want to multiply by the least common denominator. So just to verify, this particular fraction has a 2x plus 3 in the denominator. This fraction has an x minus 2. Nothing in common between these two. So we know our least common denominator is going to need both of these factors. And then notice over here, this denominator already has both of those factors. So that is our least common denominator. So I'm going to multiply both sides of this equation by that common denominator of 2x plus 3 times x minus 2. Now keep in mind, this has to be multiplied by every term in the problem. So the rational expression on the left, the original one we started with, as well as any fractions that we have on the right from structuring our partial fraction decomposition. So if we were to distribute all the way to the left-hand side, this is now in the numerator, this is in the denominator, so each of those paired factors reduces, and all we're left with is that numerator on the left-hand side. So on the left-hand side, we're just left with 4x minus 15. Now that's not going to be the case on the right-hand side. On the right-hand side, only one factor is going to reduce each time. So for our first fraction, if we were to distribute these two factors, notice we have that common factor that's going to cancel, but the x minus 2 doesn't have anything to cancel with in this fraction, so it's going to be left over. So we'll still have our a from the numerator, and then we'll also have this x minus 2. So we're going to be left with that. But again, notice the denominator did have something to reduce, so that divided out and we didn't have a denominator left. Now similarly, for this second fraction, if we distribute our least common denominator, we have a common factor of x minus 2 that divides out, but for this fraction we're left with that 2x plus 3. So for this fraction we have our numerator of b left over, and then the remaining factor of 2x plus 3. So now we have a new equation that's equivalent to the old one, just in a different form. But ultimately, we now no longer have any denominators. We have something that we can solve just straight across. So next thing I want to do is I want to distribute over here on the right-hand side. So on the left-hand side, we still have our 4x minus 15. And then on the right-hand side, I want to distribute my a and then distribute my b. So a times x, and then a times negative 2. I'm going to write that as minus 2a, just so it's a little cleaner. Then we have positive b, and then times 2 times x. So 2b represents the constant, b is an unknown constant, and then x is the actual variable in the problem. So I'm going to write this as 2b times x. And then last but not least, I have b times 3, so plus 3b. Okay, now what I want to do is I want to regroup things in a meaningful way, specifically focusing on the terms that do have an x and the terms that don't have an x. I want to rearrange things so that matching terms go together. So I still haven't done anything on the left-hand side yet, but on the right-hand side, I want to move things around and regroup them. Each term that has an x, I want to be grouped together, and then the terms that don't have x's, I also want to be grouped. So in terms of the x, we have two terms that have an x. We're not worried so much about what the other variables are. We're considering the x, the variable that creates like terms. So ax and then 2bx go together, and I'm going to put parentheses around them. So ax plus 2bx, those terms go together. And then we have a negative 2a plus 3b. Okay, now when we group these, we're going to have to be a little bit more careful. If I were to put the negative 2a first, then I may have an issue with the sign. So rather than doing that, I'm going to write a positive 3b, and I'm going to write 3b minus 2a, just to make it a little simpler. That can also be grouped, and then that's also being added. Okay, so what I now recognize is that if the left-hand side of this equation is equal to the right-hand side, then all of the corresponding matching terms have to match as well. So that means this 4x has to match up to this particular value, whatever that ends up having to be. And then the negative 15 has to match up with this. So I'm going to underline them in different ways to indicate that they match up in that particular way. Now I'm not worried so much about the x, because x is going to be the variable no matter what. What I'm trying to solve for are the values of these unknown constants. So I know if the coefficient on x on the left-hand side is a 4, then the coefficients on the other side have to combine to give me a 4. If these are the terms associated with x, and this is the term associated with x, then the 4 has to match up with the a plus 2b. So that's going to give me one of the equations in my system of equations. I'm matching up the actual constants. So I know that 4, the coefficient on x, has to match up with these coefficients on x. So it has to match up with a plus 2b. Whatever that ends up being, that needs to add up to 4. And then same thing for the constants. Negative 15 is our constant on the left, and it matches up with our constant terms on the right. And again, these look variable, but remember a and b are constants, they're just unknown. What we're focusing on is the fact that these two terms don't have an x to go with them, so they're constant. They're considered to be constant. So that means negative 15, our constant, is equal to whatever this value is. It's equal to 3b minus 2a. And that is my system of equations. We have two variables and we have two equations, which means we have enough information to solve for a and to solve for b. Now, how you go about solving at this moment is really up to you. You can solve by elimination if you want. You can use a matrix. Here, I'm just going to use substitution. So notice this a will be quick to solve for. It's easy to isolate. So I'm going to isolate that a, and that's going to be where I'm going to start. So I'm going to isolate the a by subtracting 2b. So I get that a is equal to 4 minus 2b. Okay, then I want to substitute this expression in place of a in the other equation. So we end up with negative 15 is equal to 3b minus 2 times our new expression for a, which is going to be 4 minus 2b. And now I have a new equation resulting from combining the original two that only has this one variable b. I need to solve for b. So start by distributing the negative 2. So we have negative 15 is equal to 3b. Now be careful with your signs. Negative 2 times 4 is going to be negative 8. And then negative 2 times negative 2b is going to be positive 4b. Now combine your like terms. So 3b and 4b combine to 7b. And if you want in the same step, you can go ahead and move this 8 over. So if we were to add 8, move it to the left-hand side, that's going to give us a negative 7. And then 3b plus 4b is going to give us 7b. So if this is true, then we know that b has to be equal to negative 1. So that gives us one of the values for one of the constants in our partial fraction decomposition. Now we need the value for a as well, and this is a good spot to actually find it. Notice we have an expression for a as in association with b, so a in terms of b, and it's really just one of the original equations that's been rearranged. So it's equivalent to one of the original equations. So I can sub in the value of b right there, and I can quickly solve for a. So a is equal to 4 minus 2b. We know that b is negative 1, so 4 minus 2 times negative 1. Again, be very careful with your signs here. So that's going to be 4. Negative 2 times negative 1 is positive, so 4 plus 2 which is equal to 6. So those are going to be the two constants that form this partial fraction decomposition. So my actual partial fraction decomposition, I'm going to label it PFD, my actual partial fraction decomposition is going to be these fractions with these specific values of A and B. So we determined that A is 6, so it's going to be 6 divided by 2x plus 3. And then B is -1. So either we can put a -1 here, or we could write it as a subtraction. I'm going to write it as addition and then put the -1 with B, just so it's a little clearer where that came from, and we're not just switching signs. So that is our partial fraction decomposition. Now let's verify that this is correct. So what are we ultimately saying? Ultimately, we're saying these are the two fractions that we could break this rational expression up into if we wanted to do so, which also means that if we were to recombine these using addition, then we should end up with this original rational expression that we decomposed to get this pair. So to check, let's combine these two together and verify that they do actually combine and give us this original rational expression that we had. So if we wanted to combine these two together, first thing we need to do, get that least common denominator, which is going to be 2x plus 3 times x minus 2. So multiply each fraction by whichever factor is missing in order to give us that rational expression. So this first one is missing the x minus 2. So we have 6 times x minus 2. And then I'm just going to write -1 now. So -1. And then that's multiplied by the factor we're missing over here, which is 2x plus 3. Those now combine over our common denominator of 2x plus 3 and x minus 2. So let's clean up that numerator. Distribute, so we have 6x minus 12, and then again watch your signs, both of these are going to become negative, so minus 2x minus 3, all of that is over our common denominator. Now the original rational expression had its denominator in a factored form, so we can leave this one in a factored form as well. Now we just need to combine our like terms, so 6x minus 2x is going to give us 4x, and then -12 minus 3 is going to give us -15. And again, we have that least common denominator. And if you compare this to the original rational expression, it matches the original. So that means that our partial fraction decomposition is correct. So again, how will you use this? You'll use this once you get to integral calculus. There will be certain problems you'll want to do with a rational expression like this that can't really be done with it in its current form. So if you can take the more complicated version and break it down into two individual component forms, just individual fractions that make up this more complicated rational expression, then you'll be able to work the kind of problem you need to work. So let's repeat that procedure, but let's repeat it for the more complicated ones we looked at. Okay, so here was the next one. Let's flip back over and let's find its structure. Okay, so it was this one. So we factored it, and here was our partial fraction decomposition. So linear, constant over linear, constant over linear, constant over linear, but this was a repeated factor. So the structure for our partial fraction decomposition is going to be a over x plus b over x plus 3 plus c over x plus 3 quantity squared. Okay, now same thing as before, we want to start by multiplying by the least common denominator for all of those factors in this problem. Okay, all those denominators. So if we're looking at the right-hand side, we have x, x plus 3, and then x plus 3 squared. So each one of these individual rational expressions is missing some portion of our least common denominator. It's missing at least one factor. So here we're missing two x plus 3's. Here we're missing an x, and then another x plus 3. And here we're just missing the x. So ultimately, once we multiply this whole equation, both sides, by that least common denominator. The least common denominator is going to have an x, and then it's going to have 2x plus 3's. So we're multiplying by x times x plus 3 squared in order to get everything that's represented as part of a denominator here. Now, just as before, notice that this, what we're multiplying by, is actually an equivalent form of this denominator over here. This is the factored version of this original denominator that we started with. So when we distribute this least common denominator over to the left, this denominator is completely eliminated and we're just left with whatever was in the numerator. So that's going to be 4x squared plus 10x plus 9 on the left. And then a portion of the least common denominator is going to cancel when we distribute to each of these fractions. So when we distribute here, that common x is going to cancel, but we're going to be left with x plus 3 squared. So our numerator times x plus 3 quantity squared. Now here, one of the x plus 3's is going to cancel, but we have two of them, so that leaves us with one more. And then it also leaves us with the x. So we also have b times each of those factors, so times x times the x plus 3 that's left over. And then for this last fraction, x plus 3 squared goes away, but we're left with x. So plus c times x. Okay, so now we need to distribute everything on the right-hand side. And I'm just going to leave the left side alone, and I'm not going to rewrite it. Just keep in mind it's still there. Ultimately, though, we're focused on simplifying the right-hand side. So I need to first FOIL out x plus 3 squared. I can't distribute the a until I've taken care of that exponent. So that's going to be a times x squared plus 6x plus 9. Now here, I can do a couple things. I can distribute just the x, I can distribute the bx, I can do it in one step, I can do it in two. Ultimately, it's just personal preference. I'm going to go ahead and distribute as much as I can. So I have b times x, so that's going to be b times x squared, so plus b times x squared. And then I also have b times x times 3. So we'll call that 3bx. Plus cx. Okay, and then last but not least, we need to distribute our a into what we got from the FOIL. So that's going to be a times x squared plus a times 6x, so we'll call that 6ax. Then a times 9, so plus 9a. Plus everything else we already had. So bx squared plus 3bx plus cx. So now again we want to rearrange, grouping things that go together based on the kinds of terms that we have on the left-hand side. So we have a quadratic term in x, a linear term in x, and then a constant term. So over here, we may not need to group, but we at least want to rearrange so that everything associated with quadratic x goes together, everything associated with linear x goes together, and then everything associated with the constant goes together as well. So we have two terms with a quadratic x, so ax squared, and then we also have plus bx squared, so those go together. Now we have 1, 2, 3 linear terms. So plus 6ax, let's see, plus 3bx, plus cx. Okay, so that takes care of 5 out of our 6 terms. So the only one left over is 9a, which doesn't have an x, so it's considered constant. So 9 matches with 9a, so plus 9a. So now that we know everything is matched up the way it needs to be, things are rearranged a little bit, all of the constants on the left-hand side have to correspond with the matching constants on the right-hand side. So the constant 4, the coefficient for our x squared, has to be associated with the coefficients for x squared on the right-hand side. So 4 is going to match up with a and b. 10 is going to match up with 6a and 3b and c, and then 9 matches up with 9a. So based on each of those matches for each of these individual coefficients, that's going to give us an equation in our system of equations. Okay, so we know that 4, our constant over here, has to be equal to a plus b, since these are the two coefficients for x squared. So 4 is equal to a plus b. And then 10 is equal to 6a plus 3b plus c. So 10 is equal to 6a plus 3b plus c. And then 9 is equal to 9a. Now originally you may look at this and think, okay, this is a system with 3 variables. I'm going to need a matrix. Well, look at the actual equations though. The equations are a lot simpler than typically what we use a matrix on. Specifically, look at this very last equation. This last equation already has only one variable. So you don't actually need any special technique to solve this equation. It only has the one variable. So based on that, we can just solve for a in one step. Divide the 9, which tells us that a has to be equal to 1. Okay, I'm going to box that in because things are about to get a little messy here. So we know that a is equal to 1. Well, if you look at the first equation, notice it only has 2 variables. It has the variable a and the variable b. Well, we already know what a has to be, which means we could then substitute that in here and we could solve for b. So based on that, we know that 4 is equal to 1, which is our value for a, plus b, which tells us that b is equal to, move your 1 over, 4 minus 1, b is equal to 3. Okay, so we know what a is, we know what b is, so now we know enough to solve for c. So that tells us that 10 is equal to 6a, which is 6 times 1, plus 3b, which is 3 times 3, plus c, which is still our unknown. So that means 10 is equal to 6 plus 9 plus c. Well, 6 plus 9 is 15. Take that, move it over, subtract it. So that means negative 5 is equal to c. Let me verify that. So subtract, that gives us 4. Subtract, that gives us negative 5. So there we go. So even though we had a system of 3 equations with 3 variables, just based on how simple the individual equations were, we could just use substitution here in order to solve for our constant coefficients. And that's going to give us enough information to write the full partial fraction decomposition. So let's go back to the original form. So here were our 3 fractions. We now know what those numerators have to be in order to match up right-hand side and left-hand side equivalently. So a is going to be 1, so our first fraction is going to be 1 over x. Okay, b has to be 3, so plus 3 over x plus 3. And then we know that c has to be negative 5, so plus negative 5 over x plus 3 squared. And here with this last fraction, if you want, you could write it as minus positive 5, or you can write plus negative 5, just so your constants match up a little bit more closely. But that is going to be our partial fraction decomposition. And just like with the last example, if we want, we could combine these together by getting our common denominator. And then as long as we can verify that that combination takes us back to our original rational expression, then that's our verification that this is the correct decomposition. So I'll leave that as an exercise to you. If you want to pause the video, feel free to do so and verify that. You will get back to where you started. Okay, let's look at the next one. I believe we had a quadratic factor for this one. Okay, so let's flip back over and get the form. Okay, so we factored it. The denominator was x times x squared plus 4, so linear, irreducible, quadratic, which gave us this particular form. So a over x for our linear factor, and then bx plus c for our irreducible quadratic. Okay, so our general form, a over x plus linear bx plus c over x squared plus 4. Okay, multiply both sides by our LCD to clear all of our denominators. So we have x here, we have x squared plus 4 here, nothing in common, so our least common denominator needs both of them. So we need an x and we need an x squared plus 4. Okay, we distribute that to the left-hand side. This is just another form of the denominator, so that fully cancels out, and we're just left with the numerator. So 2x squared minus 3x plus 4. Okay, on the right-hand side, partially cancels, so the x's cancel, leaving us with x squared plus 4 for this first fraction. So a times x squared plus 4. And then for our second fraction, x squared plus 4 divides out, so we have bx plus c times x. Now be careful here, make sure you put parentheses around the bx plus c as it multiplies by this x. This is going to be a reverse distribution, so if you want to rearrange it, put the x out front, that's perfectly fine. Or if you're comfortable distributing this way or maybe distributing that way, then you can leave it as is. Okay, so now the goal is to clean up the right-hand side so that we can match up all the different parts that do match. So a times x squared, a times 4, okay, and then bx times x, that's going to give us an x squared, so plus bx squared, and then c times x, so plus cx. Okay, match up everything that matches. If you want to rearrange first, you can. Here there's not a ton to rearrange, so we can do it quickly. So we have two terms that are quadratic in x, so ax squared plus bx squared. We only have one term that's linear in x, so plus cx, and then plus 4a. So based on the fact that left and right have to be in balance, all of the matching coefficients must also be in balance. So the coefficient on x squared, 2, has to match up to a and b. -3, our coefficient on x, has to match up, oops, I already put 3, so I'll put 3 here, just so that matches, my bad. And then 4 times 4a, we'll use 2 here. There we go, those have to match up as well. So we know that 2 is going to be equal to a plus b. We know that -3 has to be equal to c. Well, look at that. We don't have to do anything there. We actually know what c is already. And then 4 has to match up to 4a. So we know that 4 is equal to 4a. So 1/3 of that system has already been taken care of. We already know what c is, and ultimately c is not involved in either of the other equations, so it's independent of those two. Now this bottom equation only has the one variable, so we can solve for a. So a is going to be equal to 1. And then we can substitute that value into the first equation. So we know that 2 is equal to 1 plus b, which means that b is equal to 2 minus 1, which is 1. So we have our values for our constants, and our partial fraction decomposition results from us substituting in those values. So PFD, okay, so a over x, well a is 1, so that's going to be 1 over x, plus bx plus c. Now here b is 1, and when we sub it in, that's going to be a coefficient for x. So we don't actually need to write a 1 here. We'll just leave that as the understood one that's not written. And then c is -3, so x plus -3, we can write that as x minus 3. That's maybe a little bit nicer. And that is over our irreducible quadratic. And that's going to be our partial fraction decomposition. And again, you could check it by getting your least common denominator, combining these two together with addition, and verifying that it comes out to your original rational expression. Okay, now let's look at the last one, and then we'll look at one special case, and that'll cover partial fraction decomposition. Okay, so this was our last structure we set up. So we had an irreducible quadratic factor in the denominator that was repeated. So two linear numerators, and then one with a denominator that has an exponent of 1, one with a denominator that has an exponent of 2. So we have ax plus b divided by x squared plus 2x plus 5 plus cx plus d divided by x squared plus 2x plus 5 quantity squared. Okay, so we have 4 constants to solve for here, but don't be alarmed. Think back to how the previous 2 systems went. We ended up with really simple equations where a lot of the work was already done for us. It's going to be the same kind of thing here, so solving for these individual constants is not going to be super challenging. So we need to multiply by our least common denominator. Now notice here one of our denominators already has it, but this denominator doesn't. So this denominator needs the x squared plus 2x plus 5, whereas this one already has both of them, and then our denominator on the left already has both of them as well. So our common denominator, x squared plus 2x plus 5 quantity squared. Now distribute left-hand side, the denominator clears, and we're just left with our numerator. So 3x squared plus 8x plus 14. Okay, now for our first fraction, we only have one x squared plus 2x plus 5. Our least common denominator has 2 of them, so one factor cancels and we're left with 1. So I'm going to put parentheses around ax plus b because it's now multiplied by this trinomial. Only one of them though, because remember that denominator canceled out. So x squared plus 2x plus 5. Now this distribution is going to be a little bit cumbersome. We're just going to have to be really careful. Take our time. Okay, plus, now here again the LCD matches completely with this actual denominator, which means it completely reduces and we don't get anything extra from the least common denominator. So we're just left with the cx plus d. So plus cx plus d. Okay, so all we need to do now is do this distribution and then combine any like terms that result. So ax times x squared is going to be ax cubed. Ax times 2x is 2a, x times x is x squared, plus 2a x squared. And then ax times 5 is 5ax, so plus 5 times a times x. Now b times x squared, so plus b x squared. B times 2x plus 2b x, and then b times 5 plus 5b. And then don't forget your cx plus d, still hanging out there at the back. Now here, because we have so many terms, it will be to our benefit to rearrange things so that matching terms are grouped together. Now we only have one cubic term, and as it turns out, we don't actually have a cubic term over here. So we'll talk about what that means in just a minute. But ultimately, this is not going to group with anything else. It's already where it needs to be. So ax cubed. Now we have 2 terms that are quadratic in x. So plus 2a x squared plus bx squared. Okay. Linear, linear, and linear. Make sure you find all of them. So 5ax, 2bx, cx, plus 5ax, plus 2bx, plus cx. And it's not a bad idea, if you think it might help, to maybe check off the terms as you use them so you don't overuse anything and you don't forget anything. So we have this term, this term, this term, this term, this term, this term. So we're left with 5b and d, which don't have an x, so those are our constant terms. So plus 5b plus d. Okay, so let's match up things that match. So our 3, our quadratic coefficient, matches up with our coefficients over here. So 2a and b. Our 8 matches up with our linear coefficients. So 5a, 2b, and c. And then 14, our constant, matches up with our constants over here. Now what about this guy that's hanging out? What about that one? Well, if we were to consider this as being cubic, when it's really not, we would have to think of it as having a cubic term with a coefficient of 0, because remember, it's not really there. So if we wanted to have something to combine over here, well, then we have to think of it as 0, which is ultimately what we have to do here. In order to match up things left and right, if we have something that appears on the right that didn't appear on the left, well, that means it's associated with a coefficient of 0. So automatically, that means a is equal to 0. We actually know the value for a just based on that match right there. And then we can match up the other ones and create the equations accordingly. So 2a and b match up with 3. So 3 is equal to 2a plus b. Okay, 8 matches up with 5a, 2b, and c. So 8 is equal to 5a plus 2b plus c. And then positive 14 matches up with 5b and d. 14 matches up with 5b and d. Okay, so now let's go through this system. So we already know what a is based on that first equation, and it's okay if it's 0. That can happen. That can be a value that results. In this case, that means when we resubstitute it into the partial fraction decomposition, a will be 0, which means this linear term will actually be eliminated. It won't actually be there in the final decomposition. Now, based on that, we can then plug into the next equation, which will allow us to solve for b. So that means 3 is equal to 2 times a, which is 0, plus b. So that term is eliminated, which means b is equal to 3. Okay, so we know a, we know b. Our next equation uses a and b to find c, so we can sub in there. So 8 is equal to 5 times a, which is 0, plus 2 times b, which is 3, plus our unknown c. So that's going to be 8 is equal to 2 times 3 is 6, plus c. Subtract your 6. So c is equal to 2. Okay, and last but not least, b and d. We know what b is. So 14 is equal to 5b, which is 5 times 3, plus d. 14 is equal to 15 plus d. If we subtract our 15, move it over, that means d is equal to -1. So there are all our constants. So again, notice we had 4 equations, 4 variables, but the individual equations were so basic, we had a really good place to start, and then it just kind of builds on that, and finding the actual values is fairly straightforward. So our partial fraction, it looks like a D, partial fraction decomposition is going to take this structure and sub in all these values. Now again, a was 0, which means this linear term up here actually just goes to 0. It goes away. So all we're left with for that numerator is whatever the value for b was, which in this case was 3. So 3 divided by x squared plus 2x plus 5. And initially, that seems to kind of contradict the whole idea that if we start with a denominator that's quadratic, the numerator will be linear. Well, the structure of the numerator will be linear. But if the actual constants, one or the other, comes out to 0, then that just means that term goes away. And ultimately, that just results from the actual rational expression we're looking at, just this particular case with this particular rational expression. So there's that fraction. And then the next one, C and D, both of those are non-zero. So C is 2, D is negative 1. So 2x minus 1 is our next numerator. So plus 2x minus 1 divided by x squared plus 2x plus 5 quantity squared. That is going to be our partial fraction decomposition. And that covers all 4 that we started with. Now there's one additional situation that we haven't looked at. Before I flip over, let's go back and let's look at the original ones, the ones we just did, and think about the structure. I want you to think about how the numerator and denominator are related currently, particularly in terms of their degree. So for the first one, we had a linear numerator, and then our denominator was already factored into 2 linear factors. But if we were to redistribute, those 2 linear factors would multiply together to give us something quadratic. So we started with linear over quadratic. Okay, so the numerator had a lower degree than the denominator. Now here was quadratic over cubic, so linear has a lower degree than the denominator. And then this next one, again, quadratic over cubic, same relationship. And then this last one, the numerator was quadratic and the denominator was an irreducible quadratic squared. So ultimately the highest power would be a 4. So not quadratic over cubic, but still lower degree in the numerator, higher degree in the denominator. Well, what happens if that's reduced? So all 4, or reversed, excuse me. So all 4 of those situations, the numerator's degree was lower than the denominator's degree. Well, what if we flip that relationship? Because we haven't looked at an example where that happens. That is possible. It is possible we will run into that situation. When that is the case, when the original rational expression has a higher degree in the numerator than it does in the denominator, first thing we have to do is divide. We have to start by first dividing the polynomials. And then we go as normal and we do it exactly as we would do it before. So because here we have something quartic divided by something cubic, in a way we can think of this as not being fully reduced. This has to be fully reduced. The denominator can divide into the numerator, so we have to actually do that division in order to put the resulting rational expression in a form where we can work with it. So I'm going to divide this denominator into this numerator. Now, because we're dividing cubic and quartic, this means we're going to have to use long division. There's not going to be a shortcut here. So I'm going to set it up for my long division. Now my divisor is cubic, but I'm missing a squared term and I'm missing a constant term. So it's a good idea to put in 0 placeholders for those 2 terms that we happen to be missing, just to make our lives a little bit easier. And then that is dividing into x squared plus 3x cubed plus 6x squared plus 9x plus 4. And of course, all of the rules with polynomial division still apply. We've got to make sure all the terms are there. We've got to make sure they're in descending order based on exponent. Okay, so my first division is x cubed into x to the 4th. It goes in 1 time, so x cubed goes into the x to the 4th, x times rather. And then I'm going to multiply this portion of the quotient by my divisor, and then bring it down and subtract. So x times x cubed is going to be x to the 4th. Okay, so those terms match, they'll cancel out. X times 0x squared is 0, but let's think of it as 0x cubed, so plus 0x cubed, so that we can line things up the way they're supposed to be lined up. Now x times 4x plus 4x squared, so those line up. And then x times 0 is going to be 0, but 0x. And then we're subtracting that whole result. So So our first term is eliminated, which is the goal, and then we combine everything else. So 3x cubed minus nothing is still 3x cubed. 6x squared minus 4x squared is going to be positive 2x squared. And then 9x minus 0 is still going to be 9x. And I can bring down that remaining 4. And then I do an additional division. Now because the degrees now match, I know this will be the last division. And I also know that it's going to result in a constant, which is also an indicator that this will be the last division. So x cubed into 3x cubed, it goes in 3 times. So then 3 times our divisor, it's going to be 3x cubed. 3 times 0x squared is 0, but 0x squared. 3 times 4x is 12x. And then 3 times 0 is 0. And I'm going to subtract all of that. So my first term is eliminated. 2x squared minus nothing is still 2x squared. 9x minus 12x is negative 3x. And then 4 minus 0 is still 4. And because it's now cubic into quadratic, we know we can't actually execute that division. So what we're left with is now our remainder. So what this tells us is that this particular rational expression, another way to write this is x plus 3, which is the actual quotient that resulted from that division, plus our remainder as a fraction of our divisor. So we can't throw away the remainder here. What this now means is that this is some portion of our divisor that was left over that we couldn't actually divide out. So we're left with 2x squared minus 3x plus 4 as a fraction of our original divisor. And then this rational expression, we can now perform the partial fraction decomposition with. Now, as we perform the partial fraction decomposition, we can't forget the fact that we already divided out and we have these rational terms left over, x plus 3, where we don't actually need to do the decomposition. So don't forget these, hang on to these. I'm going to go ahead and write PFD here at the bottom, leave yourself some space. I'm going to go ahead and write it at the bottom, and I'm going to go ahead and put that x plus 3 there so that we don't forget it. Because what we're looking for is the decomposition of this original rational expression. Well, originally we divided and broke it down into something that could be divided out and then something that couldn't. And so now we have to decompose this, but we have to include the portion of this rational expression that was already taken care of via division. So we need to take this one and we're going to decompose this one. So we need to factor our denominator, and I'll just write this out to the side. So x cubed plus 4x, well, this looks familiar. So x times x squared plus 4. Okay. And then we just have our numerator. And just for the sake of checking, because this does look familiar, let's flip back over and look at the one we did that had that particular denominator. Well, hey, look at what we have. We actually have 2x squared minus 3x plus 4 over this denominator. 2x squared minus 3x plus 4 over this denominator. So actually, we already know what the partial fraction decomposition is for this one because we already decomposed it, right? This was the original one we looked at, the third one. And so because this is a term left over after the division that we just did, we already know how to decompose this one. So this one breaks down using this structure, but we already know what A, B, and C have to be based on the fact that we have these particular values. So this is going to be the decomposition for that particular rational expression. So 1 over x plus x minus 3 over x squared plus 4. 1 over x plus, I just read it out and I don't remember what I said. There we go. 1 over, there it is, 1 over x plus x minus 3 over x squared plus 4. And I'm going to write a note, part C. This was part C. We already found that one via part C. So that means our full partial fraction decomposition is going to contain those terms we got from division plus the terms we have from doing the partial fraction decomposition for this part in a prior problem. So plus 1 over x plus x minus 3 divided by x squared plus 4. That's going to be our full partial fraction decomposition. And as with any of the other problems, even though these original two terms don't have a denominator, you could still check this problem the same way. So you would still find your least common denominator, rewrite each of these with that denominator. It just means that for these two first terms, because they don't already have a denominator, they'll need both of the factors from the least common denominator. So you would have to generate actual denominators here where there are none. So you could think of it as x over 1 and 3 over 1, and then just go from there. So that gives you several different examples, different situations you run into with a partial fraction decomposition. Again, this is going to be an important skill for integral calculus once you get to that point. This idea of taking a more complicated rational expression and then breaking it down into more basic ones.